Hello, my name is Stam. I'm a researcher in graphics and AI at NVIDIA, and I'm going to talk about some research I did over the last year involving the adjoint and applying it to light transport to compute gradients. So I often get asked, what is it to do research in industry? And usually people think, the industry gives me many problems and I solve them, and some are cool and they end up in publications. Of course, this is great because we get many cool problems that we solve, and that leads in many cases to cool math. Then there are problems I just work on for fun. Okay, no one asked me to work on it. And so this work here is an example of that. And for example, people know me from my work on fluids. That's exactly it. I just worked on fluids for fun. No one asked me to do it. And then it ended up being a big feature in Maya. So what was the cool stuff I was looking at for this research? So I had done some research with the group at the University of Washington in Seattle 16 years ago on using the adjoint method to control fluids. So the adjoint method is an efficient way to compute the gradient that can then be used in optimization. And so I did that research. At the same time, I heard about the adjoint being used in rendering, something called importance, which is supposed to be the adjoint of radiance. So that got me thinking, are these two related? And so that started this research. I had no idea that it would be useful at some point or not. And it turned out it is useful. And that's the topic of this talk. So we'll be talking about the adjoint both in optimization and in rendering. So let's start by explaining how the adjoint is used in optimization. So if you understand this equality in the middle of the slide, you pretty much start to understand what the adjoint method is. Okay, at least you know what an adjoint of a matrix is, and how to take the adjoint of the multiplication of many matrices. And someone said that the adjoint method is one of the most underrated numerical algorithms of the last century. And 16 years ago, when we started to look at the adjoint method, I had never heard of it. It didn't come up in my classes as an undergrad in mathematics, so I don't think many people know about it. So usually when I work in a new field or try to understand a new technique, I start with a very simple example. And I think simple examples are good because you can visualize them, and often they already contain all the problems that can occur. And so the problem I'm going to look at, the simple example I'm going to look at, is the problem of hitting a target with a cannon. Okay, so this was an important problem, obviously, since if you could hit your enemy. And many scientists were funded by kings, of course, just like scientists are funded by the army these days. And one of the early scientists is Nicola Tartaglia, and you can see his curves weren't very correct. This was before Newton's laws were invented. And this Tartaglia also invented complex numbers. So here is the exact solution using Newton's law. And since I just mentioned complex numbers, for fun, I wrote Newton's laws using complex numbers. So this is a problem in the plane of a cannonball shot at a certain angle. And the state of the cannonball over time is represented by a point in the complex plane. And so we want to hit a target x hat. And for every angle, we end up at a point x of theta, which is the angle. And so our goal is to hit that target. And so like in any optimization problem, we have a state, which I just talked about, the position of the ball. We have a control, which in this case is the angle. We have an equation that restricts the state. And then we have a cost function. And the goal is to find the optimal angle in this case that will minimize the cost. So ideally, the cost will be 0, where we hit the target. And so here are some examples of where the ball lands for different values of the angle. So the function at the top, so this is results for different angles, okay? And the target is right in the middle, the red point. The W-like shaped curve is actually the cost function. And the red dot is where we are on that cost function for a given angle. So as we change the angle, as we go from left to right, you can see that dot on the W curve moving from left to right. And we see there are actually two solutions which correspond to the minima of this W curve. Also notice the red curve on the W curve, and that's the gradient, the slope. And this is very useful in optimization. So let's say we start anywhere on this cost function. And then by following the inverse of that slope, we slowly converge to one of the minima, depending on what side of that hump we are in the middle. And so this is basically gradient descent. They're more sophisticated techniques, but they all, if the setting is smooth, they all need the differential of the cost function with the control. So this is the quantity we wish to compute in optimization. That's sort of the holy grail. That's what we want. And we noticed that we had two minima. This is very common in optimization, where there's not one global minima. For this particular case, we can add a penalty term related to the angle, and so we prefer smaller angles, okay, which probably cost less if you try to hit a target. So in this case, we have a global minimum which corresponds to the smaller angle. Okay, so now we can generalize this problem. So this is extremely general. In fact, most optimization problems can be cast in this form, or problems in machine learning. So it's very general. It's not really an equation. It's more like a template for any problem. So we have all the ingredients. We have the state U, the control theta, the equation for the state, and we have a cost function J of U. And the goal is to find the optimal control that minimizes the cost function Ju. So it's basically a constraint optimization problem. And like I mentioned before, what we're after is computing the gradient of the cost function with respect to the controls. That's our goal. So since the state depends on the control via the equation, we can write the gradient of the cost with respect to the control using the chain rule as the product of the variation of the cost function with respect to the state times the variation of the state with respect to the control. And to make the derivations more compact in what follows, we'll use this curly delta notation, which actually means it stands for the differential of a function with respect to the control. So we use that both for the cost and for the state. So that allows us to write the equation at the top more compactly than the one at the bottom. And in what follows, we will show two techniques to compute this gradient. Since we have that the equation is 0, then it naturally follows that its differential with respect to the control is also equal to 0. Again, we use the chain rule, and what we get is a linear system for the delta U. And once we have the delta U, we solve the linear system, we can compute the gradient. So it's very straightforward. But now we will look at another technique. So this is called the forward method, and you'll see why. Another technique is called the reverse method. And here we introduce a new variable P, which is the adjoint state, and it satisfies another linear system, which is constructed from using the EU from the forward method, but taking the transpose and making it equal to minus the derivative of the cost with respect to the state. And if we solve that equation, we can use P to solve the gradient in the following way. We just multiply P transpose times the derivative of the equation with respect to the control. And I claim that you actually get the same gradient. And it's a very easy proof. It's a one-liner. I can give it here. So we start with the expression we had for the gradient. We replace Ju by its expression from the adjoint equation. We transpose that, and then we factor the transpose, so we reverse the order. And then we recognize that EU du is actually the linear equation, which is equal to E, the derivative of E with respect to the control. And so we get the expression. So it's a very easy proof that shows that this is an alternate way of computing the gradient. And for those of you who know the theory of constraint optimization, P is actually the Lagrange multiplier. So why did we introduce the reverse method? Well, it's much more efficient. And the way to see that is that the reverse equation does not depend on the controls. So if you have one control or a million controls, the cost will be exactly the same. And this is the main advantage of using the reverse technique. And I can visualize this here just by showing the sizes of the vectors involved. You can see that the delta U is very fat. It's as wide as there are controls. And the P is very slim. Actually, it's of size 1. Okay, I have to make it a little bit bigger so you can see the P in it. So the 1 is actually big. Now, geometrically, what does the adjoint method correspond to? So people are used to Lagrange multipliers, and that's actually what the adjoint is a Lagrange multiplier. Is in constraint optimization, the solutions are where the gradient of the cost is collinear with the gradient of the equation of the constraint function. So in this case, the constraint is a circular field. And so where these two gradients are aligned, there's a solution. And of course, there's not a single solution. In fact, there are many points in this field where these vectors are collinear, but the point has to be on the constraint as well. And usually you can, even then you can have a few of them. So you choose the smallest one. So here I want to give you an analogy, which is kind of fun that I came up. It's a made-up example. And so here's the problem. So you're in your basement, you have a safe, but you left your key upstairs. And you want the gold that's in the safe. So there are two techniques. The forward technique is you carry your safe upstairs, use the key and get your gold. The reverse technique is you walk upstairs, you get your key, you walk downstairs, and you open your safe and you get the gold. Obviously, the second approach is way more efficient. Okay, the second approach is where you use the adjoint. And so going up the stairs is solving the linear system, the forward system. Going down the stairs is to solve the adjoint system. Your safe is the delta U, which is big if you have a lot of controls. And the adjoint is very lightweight. Okay, it's a key. And of course, the cost is the gold, which here is more like the benefit. But anyway, this is kind of a fun example to keep in mind. Okay, this was all I wanted to say on the adjoint technique, how to compute the adjoint, how to use the adjoint to compute the gradient. Now I'm going to give a little overview of the adjoint in light transport. So in light transport, the basic problem is we have some light emitters, and we want to figure out how much light reaches a receiver, typically a camera. And so the light from the emitter bounces between surfaces and eventually reaches the receiver. So we model the light is modeled by radiance, which we denote by L. Light sources are L0, denoted by L0. And every scatter event, of course, involves BRDFs, BTDFs, and whatnot. But here we just want to look at the structure of the problem, so we model that by an operator T that modifies L and returns a radiance. And then the basic equation is, it's an equation, it's L is equal to the direct light plus the scattered light. And this is an equation because L appears on both sides of the equation. Now the adjoint problem, what it's called, is to solve for the importance. And the importance is, at every point in the scene, tells us how that surface is important at illuminating the receiver. So let's say you have a separate room that's completely shut down, all the windows are shut, then the importance in that room is 0, because no light will affect the receiver. And so it's adjoint to the radiance, and actually it travels in the opposite direction in a sense. So you start from the receiver, so it's essentially ray tracing from the eye, and then you propagate the importance. And it scatters as well at surfaces, and it's actually the adjoint of the transport operator scatters the importance. And we get a similar equation for the importance. The only difference is that we have the adjoint of the transport operator. So here we see what's happening. So radiance gets propagated from the emitter to the receiver, and importance gets propagated from the receiver to the emitter. And both satisfy these equations. Now it turns out that we can solve these equations formally. And we can do that by just putting all the terms of L on one side and then taking the inverse. So we have to take the inverse of 1 minus T inverse, and that's just, we can use a power series. It's called the Neumann series. And we can do the same for the importance. And so if we group all these terms together in a single operator S, which we can call the scattering operator, we see a direct relationship between the source intensity or the source radiance and the radiance at the receiver. And the same for the importance, where in this case it's the adjoint. And you can see it's quite intuitive why we get these powers, which correspond to many scattering. It corresponds to how many times a ray scatters between the surfaces before it reaches the receiver, or the other way for the importance. And what we're interested in is a measurement of the radiance. So usually to get a measurement, let's say at the receiver, we convolve the radiance with some filter W0, which we said was the source for the importance. And again, by the definition of the adjoint operator, we can compute this intensity either at the receiver or at the emitter. So at the receiver, you use the radiance propagated, and at the emitter, you use the importance that was propagated in the other direction with the source. And because these operators are adjoint of each other, these intensities are the same. So this, in summary, is the role of the adjoint in light transport. Very short summary, but that's all we need to show the link. So now let's combine what we talked about in optimization and our brief introduction to light transport. So we go back to optimization. So I recall the basic equation or the basic template of optimization, and now we just replace the state by the radiance. That's our state. The control could be anything, could be the material properties, for example, or the emission of a light source. And so those are sort of the parameters we want to learn. The equation is just a transport equation, with the transport now depending on the controls, and the light sources depend on some controls. And the cost is some function of the intensity. Okay. And so what we want to compute is the differential of the cost function with the controls. Again, with the chain rule, we can relate it to the differential of the radiance with respect to the controls. And that's the quantity we're interested in computing. So we now have our expression for the equation. And so all we have to do is take the differential of the equation with respect to the radiance. That's quite easy to compute because it's a fairly simple equation. And so we just take ddl of minus L plus, and we assume that the transport is linear, so it doesn't depend on L. And what we end up getting is minus the identity plus the transport operator. And we can easily take the transpose. The transpose of the identity is the identity, and then we take the transpose of the transport equation. Okay, so now if we, and that's how we obtain an equation for P. So P is not the radiance, it's not the importance, it's a new quantity, a new function, which is the adjoint. And if we look at this equation, if we write it out, now we know what EL star is, it's actually exactly the equation for the importance with a different source term, which is minus the gradient of the cost function with respect to the radiance. And so this is the fundamental equation of this talk. Okay, why is it so cool? Is that to compute the adjoint, we can reuse the code that computes the importance. So that's really the beauty of this. So by doing the derivation, it shows that we can reuse the existing code already. And so this is how it works. We go from the receiver to the emitter. And just like we did for the importance. And we use the adjoint transport operator. Okay, so this gives us the adjoint. But what about the gradient? Well, here we use that expression for the gradient that we showed was equivalent to the one obtained with the chain rule. And so all we have to compute is the derivative of the transport equation with the control this time. That's shown at the bottom. And then we multiply that by the adjoint. And that's the expression we get. And so we compute this gradient as we compute the adjoint, going in reverse. So here we put everything together. So there are two passes. In the first pass, we compute the radiance from the light sources to the receiver. Then at the receiver, we compute the intensity, the cost function, and then we do a backward pass where we set the initial adjoint to minus the gradient of that cost function we just computed with respect to the radiance, and then we propagate it backwards using the equation for the importance. And at the same time, we update the gradient of the radiance with respect to the controls. And then at the light source, we obtain this gradient that we're after. So anyone who knows about deep learning and who does it these days notices that this is very similar to the way a neural network works. So there's a forward propagation. So where the weights are the controls this time. And the equation is just y equals f of x, outputs equals a function of the inputs via the network. And then we compute a gradient using back propagation. In fact, in neural networks, you combine the computation of the gradient and gradient descent at the same time. So as you propagate backwards, you're updating the weights as well. Okay, so this is one way of computing the gradient. It involves a lot of math. What's more popular these days is to actually, you take your equation, you discretize it, and then you use automatic differentiation to get a version of your code that computes the gradient as well. Okay, and there are many tools out there. I've listed a few of them here. So we could have used this. The problem is that the nice thing of our approach is that you can reuse the existing renderer. And every time you improve your renderer, automatically it will improve the computation of your adjoint. And you don't need to recompile all your code to get the differential version. So there are basically two approaches to computing a gradient. You can use the AutoGrad approach, and that's called discretize then optimize. So you discretize your problem and then you compute the gradient of your code. Our approach is called optimize and discretize. So we derive an equation for the adjoint, and then we discretize that equation. And this is summarized in this slide. So the cloud is sort of, we live in the math world, and the computer screen there is sort of, we deal with code. So in DTO, we discretize a problem, we get solver code, and then we translate that into adjoint code. And in OTD, we derive in the math world an equation for the adjoint, and then we discretize the adjoint. So here we unfold this a little bit. And what we show here is, and that's what I talked about before, is that when you're solving for the adjoint equation, you can reuse the same code, the exact same code, in the case of the renderer. So, of course, if your code doesn't come from an equation, then you have to use the automatic differentiation technique. But if your problem comes from an equation, or from EU equals 0, then this technique is much more efficient and much more elegant, I think. Okay, so I had to implement this technique. Actually, it's very important to implement a technique. You can do all the math, but if you don't implement it, you're never sure if your math doesn't have any mistakes in it. And so I could have implemented in one of the existing renderers that are out there, but I decided to write my own because it's more fun and simple, and I wouldn't have to deal with how to port things. And anyway, and it's actually fairly simple to write a path tracer. So this is my program. So it's good, you can visualize all the different paths and everything. And the code is actually quite simple. So this is the main routine. It basically loops over all the pixels of an image and then creates a path in the scene. And then there's a forward path, and it's an option to compute the gradient. So if the user wants a gradient, then you perform a backward path, computing the adjoint and the gradient. So here is just the make path is just the usual. It's very simple. It's just a recursive call over all the objects in the scene. So it's not efficient. It's just very. I wrote this code just as a proof of concept, and it was fun to do anyway. So here's the forward path. So this assumes you have a path computed. So of course it's not efficient. And you perform a forward path. And here we perform a backward path. So here are some results. They actually look like images made in the 80s. That's because my path tracer is so slow. So what I'm showing here is, of course, the rendering at the top left. And then I'm showing the gradient with respect to different controls. So the controls here are the parameters of the reflection models. So the walls are diffuse. So there's an emission parameter and a diffuse parameter. Then there's a light source that has only an emission parameter, and then a Fong-Blin model for the sphere. So that has like 3 parameters. And so here I show the gradient for all of these. Okay, so these are just pictures. How do we know that they're actually the right gradients? So we use finite differences. So the way it works is we run the path tracer by perturbing one of the controls by an epsilon, by plus the epsilon and minus the epsilon, then we divide by 2 epsilon. And that's how we can estimate the gradient. And then we compare it to the gradient that we compute directly using the adjoint tracing. And so our results are at the top there, where it says dj divided by d control. And the problem with finite differences is that the results depend on your epsilon. So if you choose your epsilon too small, as you can see on the right, they're all 0. So that's too small. And then it's sort of a sweet point. So if the epsilon is too big, it's not precise enough. So in between, we get good agreement with our results. And this was actually very useful because we found some bugs in the math this way. So it's very important not just to show the pictures, especially in these cases where you're trying to optimize, right? Your results have to be accurate. So sorry, I don't have some beautiful pictures, but at least, this helped me to validate my model. Okay, I have to mention that there's another paper, or actually there is a paper at SIGGRAPH that does exactly the same thing. And this is work by the group of Wenzel Jacob at EPFL, and I believe Merlin is going to give the talk at SIGGRAPH. And what they showed, so what's interesting, at the beginning of this talk I said I just did this for fun, right? But they did it out of necessity. So they used the sort of AutoGrad method first in their Mitsuba software, and they found it was way too slow. So they had to find an alternative, and they came up with this technique, which is exactly the same thing, the same idea. So using the adjoint method, and then noticing that it's the same as computing the importance, just with a different source term. And what's great is that they actually proved that it was 3 orders of magnitude faster than what they had before. So it's a really useful technique, even though at the beginning I did not know it would result in something very efficient. So it's interesting how we came to the same result from different motivations, which is kind of interesting. And so if you want to know more about this technique, I put my paper on arXiv. It's under review right now for a journal. But the paper is there. You can find all the details, a lot more than I've given in this talk. And so, yeah, please check it out if you're interested. And with that, I want to thank you for your attention and enjoy this virtual SIGGRAPH.